Welcome back to my podcast episode 2. I hope you learned something from the previous podcast video. It is a very great honor to share with you the content of Malaysian Secondary School Physics syllabus. I am very grateful if you can like this podcast and subscribe to my channel to motivate me in producing more podcasts in the future. Today I am going to share with you a topic in Form 4 syllabus which is momentum. First of all, what do we understand about momentum? The word momentum originates from Latin that means movement. Isaac Newton described it as a quantity of motion. In the end of this podcast, you will be able to define momentum, set the principal conservations of momentum. Number 3, explain situations and solve problems involving elastic collisions, inelastic collisions, explosion. Number 4, explain applications related to principal conservations of momentum. Now let's imagine that a fast-moving car and a lorry carrying a heavy load moving on the road. It is found that the lorry carrying heavy load is more difficult to stop if both vehicles are driven at the same velocity. This is because the lorry possesses more momentum than the car. An object is moving with a high velocity or an object has large mass will have a larger momentum. Momentum is a vector quantity. Do not forget that vector quantity means the physical quantity consists of both directions and magnitude. The directions of momentum is the same as the directions of the velocity of the object. Now, here's the fact. All moving objects have momentum. Momentum is defined as the product of mass and velocity. The formula is P is equals to mv, where P is momentum, m is mass, and v is velocity. The SI unit for momentum is kilogram meter per second. Remember, in problems related to momentum, we will have to consider the positive signs as the object moving to the right and negative signs as the object is moving to the left. Now, let's try one example questions related to momentum. Okay, now let's look at this first example. A lorry of mass 20,000 kg moves with a velocity of 22 meter per second. A car of mass 2,000 kg moves with a velocity of 30 meter per second. What is the momentum of the car and the lorry? So first thing is we are trying to find the momentum of the lorry first, yeah? So first thing, we just take down the information that's given to us. So we have mass of the lorry is 20,000 kg, and then velocity of the lorry is v is equal to 22 meter per second. Next, we use the formula P is equals to mv to find the value. Okay, next we have P is equal to mv. Then we substitute 20,000 times 22, we have 440,000 kilogram meter per second. Now, how about the car? Same, we just apply P is equal to mv and then we just substitute the mass is equals to 2,000 kg and then the velocity with 330 meter per second. Then we'll get 60,000 kilogram meter per second. Okay, now next question we see here. Now, B, if the lorry moves with the same velocity as the car, what is the momentum of the lorry? Now, here they just change a little bit the value of the velocity. So, the value of the velocity is 30 meter per second. The mass of the lorry is 20,000 kg. So, we just substitute P is equals to mv. And here we are going to get 20,000 multiplied with 30 and then you'll get 600,000 kilogram meter per second. Now, next we are going to talk about the principal conservations of momentum. What is principal conservations of momentum? The study of the concept of momentum is important for predicting the motions of an object after the occurrence of a collision. The term conservations is used if the total amount of matter or quantity remains the same before and after the occurrence of an event. Okay, the principal conservations of momentum states that the total momentum of a closed system is constant if no external forces act on the system. I repeat, The principal conservations of momentum states that the total momentum of a closed system is constant if no external force acts on the system. This means that the total momentum before the collisions is equal to the total momentum after the collisions, if no external forces act on the system. To be precise, the principal conservations of momentum is true for a closed system. I repeat, a closed system. Okay, so what do we mean by closed system? A closed system is one with the sum of external forces acting on the system is zero. For example, the frictional force is an external force, and the frictional force acted on the system is zero. Moving on, now I want to introduce you to three types of situations in the study of momentum. Number one, elastic collision. Number two, inelastic collision. Number three, explosion. In an elastic collision, two objects collide will move apart after collisions. In these situations, the total initial momentum is equals to m1u1 plus m2u2. After the collisions, the total final momentum will become m1v1 plus m2v2. If we combine the equation, it will become m1u1 plus m2u2 is equals to m1v1 plus m2v2. Hence, the total momentum is conserved. The common observed situations for elastic collisions are Newton's cradle balance ball and a snooker. Next, we will look at inelastic collisions. In the inelastic collision, two objects combine and stopped or moved together with common velocity after the collision. In this situation, the total initial momentum is equal to m1u1 plus m2u2. After the collisions, the total final momentum will become m1 plus m2 multiplied with v2. So if we combine the equation, it will become m1 u1 plus m2 u2 equals to m1 plus m2 multiplied with v2. In this situation, the total momentum is also conserved. Now we will look into explosion. When we talk about explosion, maybe it is easier if we look into the situations of launching of a rocket. Launching of a rocket is an example of explosion. Explosion refers to a situations when an object at rest breaks into two or more parts. Before launch, the rocket is at rest at the base of the launch pad with zero momentum. During the launch, hot gases move downwards and the rocket moves upwards. Now, if we relate the situation with the formula, it will be like this. Before launching, the total momentum is zero because the velocity is zero. By referring to the formula of momentum, P is equals to mv, we know that P will become zero. After the explosion, the momentum will become m1v1 plus m2v2. Hence, the principal conservations of momentum will become 0 is equals to m1v1 plus m2v2. The total momentum is also conserved in explosion. Here, I want to emphasize that the directions of the motions of the object are still very important. We will have to consider the object that moves to the left and downward is denoted with negative sign, and the object that moves to the right and upward is denoted with a positive sign. The positive and negative sign is very important in problem solving involving the calculations of momentum. Now let's look into few examples of problem solving involving momentum. Okay, now let's look at this example. Jane and John go ice skating. With the skates on, Jane and John pushes against each other on level ice. Jane of mass 50 kg moves away at a velocity of 3 meters per second to the right. What is John's velocity if he is 75 kg? Okay, now if you look at this situation, originally Jane and John are sticking with each other, and after that they'll push away each other. So in this situation, it is related to principal conservations that is related to explosion. Now, first thing is we let V is equals to the velocity of John. Then we know that from principal conservation related to explosion, we know that total momentum after explosion is equals to total momentum before explosion. If you want to write total momentum before explosion equals to the total momentum after the explosion, also correct, no problem. Next one, I'll just apply the formula inside. I'll get m1 v1 plus m2 v2 is equals to 0. Then I substitute the value inside. I get 50 times 3 plus 75 times v is equals to 0. Next one, I just rearrange the formula and I'll get v is equals to 150 over negative 75 and I get negative 2 meter per second. So what does the negative means here? Now, the negative means here, John moves to the left and opposite to Jane's motion. Okay, so that's why I said the negative sign is very important in the topic related to principal conservations of momentum. So next example we'll see like this. Before collision and after collision. I give you a diagram where I have a small ball which u1 is equal to 10 meter per second. Is colliding with a ball, a big ball which is stationary. And then after the collision, we can see that both of the ball are moving together. Okay, are moving together. So next thing is, we know that total momentum before the collision is equal to the total momentum after the collision. So because it is in elastic collision, that's why the formula is like this. m1 u1 plus m2 u2 is equal to m1 plus m2 in the bracket multiply with v2. Then I just substitute my mass. m1 is 2 kg, m2 is 3 kg, and then my u1 is 10 meter per second. My u2 is 0 because the ball is stationary. Okay, and then last one I just substitute inside and I'll get this formula. 2 times 10 plus 3 times 0 is equal to 2 plus 3 multiplied with v. Then after that I'll get 20 is equals to 5v. Okay, 5v. Then I just rearrange it. I'll get v is equals to 20 over 5 and I get 4 meter per second. So this is how I get the answer to find the problem involving inelastic collision. Now next we are going to see another example where you can see the first ball, the big ball, okay, is moving to the right and then the small ball is moving to the left. Okay, both have velocity. And after the collision, the two of the ball are not sticking together, they are separate. So in this situation, we can see that it is an elastic collision. So total momentum before collision is equal to total momentum after the collision. Then how is the formula? So how do you write the formula? The formula is like this. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Now we have to take into the consideration of the second ball. You see the ball with 1 kg is moving to the left. That's why the velocity becomes u2 is equal to negative 2 meter per second. Then I just substitute inside whatever the information I have. Mass 1, 2 kg multiplied with 10 plus 1 kg multiplied with negative 2 is equals to 2 times 6, okay, meter per second plus 1 times v2 so that I can find v2. So again, I rearrange the formula and then I'll get this. Next one, I'll get v2 is equals to 18 minus 2 is equal to 6 meter per second. So again, I have to emphasize that in this question, you have to identify how is the movement of the ball after the collision. So here I know that it is an elastic collision, that's why I'm using m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Okay, I hope that you can understand how to do problem solving for question involving principal conservations of momentum. Okay, you may watch this podcast again if you are still not confident how to use the formula of principal conservations of momentum. Moving on. Now I will talk about 6 applications of principal conservations of momentum. The first one, the rocket. The rocket works according to the principal conservations of momentum. The fuel, a mixture of oxygen and hydrogen, are pumped into the combustion chamber. The mixture is burned in the combustion chamber. This combustion produces exhaust gases at high temperature and high pressure. The gases are expelled from the exhaust at a very high velocity, thus producing a large momentum backwards. A forward thrust of momentum of the same magnitude is produced on the rocket in the opposite directions. This will propel the rocket with an increasing acceleration to the sky because the mass of the fuel is decreasing. Thus, the mass of the rocket decreases. Next, the lower part of the rocket separates when the fuel inside is used up. The density of air decreases, hence the resistance of the rocket also decreases. The gravitational acceleration decreases when the rocket is getting further away from the Earth. Number two, the jet engine. The principle of the jet engine is actually depend on principal conservations of momentum. The fuel used is kerosene and the oxygen supplied from the air helps the combustion. When the engine is ignited, the air is sucked in from the front part, then it is compressed and pushed into the combustion chamber. In the combustion chamber, the air is mixed with kerosene vapor. When the mixture is burnt, hot exhaust gases at high temperature and high pressure are produced. The hot gases expand and are expelled from the back at high speed. The exhaust gas produce equal and opposite momentum to propel the jet engine forward. Number three, technique in soccer ball. Do you realize a soccer player runs before kicking the ball? It is because the ball can be kicked further in this method compared to the ball kicked by a player who is not running. So this is because a bigger momentum is produced when running and this momentum is transferred to the ball. Number four, the cuttlefish. The cuttlefish ejects a big volume of black ink backwards at a high pressure to escape from its enemies. This produces a backward momentum. The backward momentum will produce a forward thrust at the cuttlefish. This obeys the principal conservations of momentum, which the momentum of the system is zero. The fifth application is the wooden boat in the swamp. If you look at the figure, you can see that a big fan is set behind the boat. The fan will propel and produce a great wind backward which pushes the boat forward. The applications applies the principal conservations of momentum. Last but not least, the water hose. Let's look at the figure. Firemen are trying to put out a fire. The firemen in the figure are thrown backwards when the water at a high speed gushes out of the hose. Water gushing out of the hose at high speed has a high forward momentum. Due to this, two or more firemen are needed to balance the momentum by holding the hose tightly. Okay, before I end my podcast, let's revise again some of the important facts here. Number one, the definitions of momentum. Momentum is defined as the product of mass and velocity, where the formula is P is equals to mv. Number two, the principal conservations of momentum states that the total momentum of a closed system is constant if no external force acts on the system. Number three, we have situations involving elastic collision, inelastic collisions, and explosions and their formula. Number four, the applications of principal conservations of momentum that is introduced to you are number one, rocket, number two, jet engine, number three, technique in soccer ball, number four, cuttlefish, number five, the wooden boat in the swamp, and number six, the water hose used by the fireman. I have come to the end of this episode podcast. I hope you enjoy my podcast video. Don't forget to like and subscribe for more podcasts in the future. See you next time. Bye.